Hello and welcome to today's video. So this is homework number 2 in your booklet, and today we're going to look at bitmap images. Now before we get started, look at the criteria on the starter task and please tick bronze, silver or gold for each of the criteria on the before part of the table. Okay, so now you've done that, let's get started. So if you haven't already, please subscribe to my channel. If you are watching from elsewhere, visit my shop on Tess, and also you can follow me on Twitter as ICT and Computer Science with Miss Price, or at Miss Price CSCI. Okay, so how are bitmap images encoded? This is what we're going to look at. Now, if you're in my Year 12 class, you would have looked at this last year and it's probably just a matter of revising it, let's hope. So, but anyway, let's discuss how bitmap images are encoded. So you can see that I've got all the stimuli to the right here. If you haven't guessed already, bitmap images are simply made up of pixels. Now, pixels is just an abbreviation for picture elements, okay? And they can either be these little squares, or they can be these little round circles. So images are stored as a 2D matrix, meaning that they've got some kind of coordinates. So they can take different shapes. So if you can see the image here, you can see those ones over here, kind of more rounded, and these ones here are more square. So how are they encoded? Well, hopefully the stimuli has already given you an example of that. They're simply coded and they're organised as a grid of coloured squares. That's all they are. So when you're actually looking at any kind of image, really, it's simply just an illusion, okay? It's not really the image. It can be a grid like this one you're seeing right here, that's just simply a bunch of colours, okay? And every single different square is a different colour. Or it can simply be just a whole bunch of lines and circles that are just simply on an axis. So now each colour is stored as a binary number. So again, this adds to the illusion. Are you looking at a colour or are you looking at a number? That's what you're looking at. You're just simply looking at numbers. They're just encoded. So as you can see, the white colour is 0 and the black colour is simply, sorry, that shouldn't be a bracket there, that should be 0. Is a 1. Now, estimating file sizes. So because bitmap images are pixels that are just simply made up of, coordinates, they are rather big file sizes. So when we estimate the file size of a bitmap image, you need to consider the following: image resolution, the number of pixels that make up the image, the bit depth, that's the number of bits used to represent the smallest unit. And so if we take a look at bit depth, the colour depth of an image is measured in bits. Okay, so the number of bits that indicates how many colours are available for each of those pixels. Now, this one is only 2 colours, so therefore it's just 1 bit. Okay, because 2 colours make 1 bit. So 2 bits of colour depth will allow 4 colours. Okay, so if we take a look at the colour depth when estimating, and all you've got to do is simply just multiply it. And it goes on and on, obviously. This is just an example. So 1 bit is 2 to the power of 1, so that's 2. And 2 bits, which we saw here, because there's white and black, is 2 to the power of 2, which means 4, so that will allow 4 colours. Okay, so 3 bits would be 2 to the power of 3, and so on and so forth. Now, estimating file sizes, again, we need to consider resolution. Now, resolution is something that you come across quite a lot, okay? Maybe you don't realise it or you don't actually think about it. But every time you go into, a massive shop like MediaMarkt, El Corte Inglés or John Lewis, they've always got like these massive TVs. And you see on these massive TVs the number of pixels that they have. But just by looking at the TVs, and what you probably learn very quickly is the more pixels there are, the better the resolution, okay? The more colour depth, the clearer the image is, okay? So if we look at this TV here, and I know it's not a very good picture, but it's 1080 pixels in length, and then 1920 pixels wide. Okay, so that is how many pixels are actually in that TV. Now, obviously, the more there are, the smaller the pixel, so then the better the quality of the image and the better the illusion, okay, better the resolution. So as we can see, the resolution is measured in pixels, and then it's dots per inch. So when you see DPI, that simply means dots, density in dots per inch. And we're going to put this into perspective. There's a website, obviously. Now, a website needs to download their images very, very quickly. You're not going to wait, well, I think it's more than 10 seconds for an image to load up on a website. You'll just simply go somewhere else. So to put this in perspective, DPI means, say, if we've got resolution DPI, this means that this image has 72 pixels height and 72 pixels wide. Okay, and that's not a lot. So 72 times 72 is 5,184. Okay, so that's how we figure it out. So the higher the quality publications, such as magazines, okay, because magazines are obviously very glossy, they've got to make the images look absolutely fantastic. Okay, so they've got a resolution of 600 DPI. So if we do 600 times 600, how many pixels do you think would be in that image, or can you calculate would be in that image? Now, difference between vector and bitmap. As I said, when you look at an image, it's just an illusion, okay? It's just a representation. So we know that the bitmap is made of, you know, units of pixels, okay, picture elements. Now, vector is made up of points and curves, okay? So that's why that when you download a bitmap and you stretch it, you're actually stretching. It's not going to all of a sudden, like just because you've stretched an image, it's not going to develop more pixels. It'll just make these pixels bigger, and that's why they look like the little squares that you see here, and the quality of the image gets worse. Now, when you download a clip art image, so for example, if you use something like PowerPoint like I use, and you download a clip art, they're made up of vector. So when you stretch out a vector, it never loses quality, okay? Because like I said, it's just points and curves. Well, points and curves can move, and they can be stretched. So, bitmap versus vector. Now, bitmaps will use less processing power than a vector, and a vector will use more processing power. A bitmap is made up from pixels, vectors are made up from lines and curves. Each individual element cannot be grouped in a bitmap because they're tiny pixels, tiny pixels. But a vector, the elements can be grouped. Images are less precise than vectors because, as we know, they're simply pixels on a grid. But vectors are more precise because they're created from mathematical calculations. Bitmap will use more memory and storage because it's got all those tiny pixels to store. But a vector will take up less storage space because all it's doing is simply storing mathematical calculations. Now, choosing correct format, okay? So when do I choose a vector and when do I choose a bitmap? Well, both of them have their place, okay? But what you may be asked in the exam is they're going to give you a scenario and you've got to be able to confidently choose whether you want a bitmap or whether you want a vector, okay? And you've got to be able to justify your choice. So now resizing an image, so that would obviously be a vector. So if they give you a scenario saying, Katie is going to design a poster and she is going to put a logo on that poster, but she may want to resize the logo because she hasn't decided whether she wants it to be covering the whole page or just part of it. Which image type would she choose? Well, she can choose a vector because then she can make it as bigger or as smaller as she wants. Scaling, drawing. Now, if you're going to scale a drawing, the best format would be a vector, and that's because they are created using mathematical calculations. Realistic images, the best format would be bitmap. Now for that reason, it's because it can have lots of color depth, okay? Now, typical software features. Now, there's many different softwares out there. So you've got professional softwares such as Photoshop. Then you've got other softwares that can be downloaded for free. And also you may have software already on your computer, like Paint and, you know, so on and so forth. GIMP is a free software, and it's kind of like a version of Photoshop. So layers. Now they always have layers, okay? So some of the layers can be made transparent. They can be put on top of each other, so then you can create your own image. Cropping, you can always crop out parts of an image. Most softwares offer these. Resizing, so you can make an image bigger or smaller. Stretching, so basically you can make an image look stretched in or, you know, pulled out, whatever you want to do with it. You can rotate an image, so you can make it turn upside down. Also, you can mirror an image, because sometimes an image may be facing the wrong way. You might want it, like for example, we've got our dog here, it's facing to the left. We might want him to face to the right. Now, if we try and do that, he might be upside down, but you can actually mirror the image and flip it round. And then here, you've got rotation here as well. Okay, now points to consider for the exam is bitmaps are made up from individual pixels. Each pixel is a addressable unit which allows subtle changes to be made into the image. The bitmaps can be compressed to reduce the file size, but this may result in loss of detail. Okay, so it may become a bit more pixelated, or you may lose depth of color. Each pixel represents a color, so every pixel can be a different color, and this can result in very high quality detailed images. Now, bitmaps take up a lot of storage spaces. The information needs to be stored for every single pixel, and that's a lot of pixels, as we know. And now large bitmaps can take a long time to open and load. So the more pixels, the better the resolution and the better the quality of the image is always the rule. Okay, no matter the file. Right, so let's take a look at some exam questions. Okay, so now these are the types of questions that you could be asked. So what we need to bear in mind is that you need to know your numbers. For year 12 and year 13, you need to know your numbers. The numbers, the data representation, which is the binary, whether that's going to be 8-bit, 12-bit, and so on. 2's complement, binary coded decimal, ASCII. Sometimes these questions end up all fusing into one. Okay. Now, as I've always shown you, it's not a matter of answering one question and moving on. You'll find each question's interconnected. Okay. So anyway, I'm going to go through this question with you. So I'm going to draw here, and I'm going to use my wonderful graphics tablet that makes me write not so neatly. Okay, so I didn't want the menu there in my way, but it looks like it's going to be. So anyway, right, we've got a touchscreen as 3 squares where selection can be made. So you've got ST and you've got U. The X coordinate, the center of the 3 squares, is held in 3 memory locations, as you can see right here. So, this is ultra sensitive. So now give the hexadecimal value for each content for U. Now this is really easy. So it wants the content right here for, So it wants the content right here for U. Okay, so you can see here that these are simply binary. Now these are just 4 bits. Is all you've got to do is take these 4 bits here. Look, so this one is 0, 0, 1, 1. Right, so that would be 1, that would be 2, that would be 4, that would be 8. Now remember, it wants it in hex, okay? So 8, now we don't need to add the zeros, do we? We know that. So 8 add 4 is 12. Now we know that in hexadecimal, 10 is A and 11 is B and 12 is C. Okay, so that's going to be C. So the first thing I'm going to write down here is C in my very messy graphics tablet handwriting. And then I'm going to do the same thing here for this one. Okay, so 0, 1, 1, 0. We know that's 1. We know that's 2. We know that's 4. We know that's 8. 2 add 4, okay, is 6. Then we're going to do the same here. Right, so 1, 2, 4. So in hex, that is going to be, I'm going to try and write this neater, 4, 6, C. Okay, 1 mark is what you get for that. Now convert the denary number 40 into binary. Now, if you don't know how to do this by now, I won't be happy. Right, I'm just going to clear some space here. Okay. Oh dear. Right, in fact, I'm just going to clear all the drawings. Right, there we go. And I'm going to start with this one right here. Okay. So let's draw. Right, so 40 into binary. Well, that is an easy 1 mark. So I'm going to draw my little table that I like to draw. 8, 16, 32. I don't think we need to go any further than 32, do we? We know what to do. Okay. Right. We know that's going to be too much. 32 add 8 is 40. There we go. Okay, so we know this is 0, 0. So I hate this graphics tablet. I need to do something about this. 1. There we go. 1 mark. Okay, done. Let's look at the next question. Okay. Bitmap graphics are used to represent squares S, T, and U. These can be saved in a different number of image resolutions. Give the number of bits required to store each pixel for a black and white bitmap. Oh, we've just been through that, haven't we? Okay. Black and white bitmaps. So there's only 2. So 2 colors. So that's 2 times 2. 2 to the power of 2 is, and I'm just going to double check this. So 2 to the power of 2. Now, you're not allowed a calculator in the exam, but we're not in the exam right now, and I'm going to go 2 times 2, and it's 4. Okay, so it'd be 4 colours needed. So I'm going to say the number of bits required. Okay, for give that anyone. Oh, S, T, and U. Okay, so yeah, 2. Yeah. Okay, so it will be 8. Okay, 8 bits would be required. Sorry, S, T, and U, so that's 8 bits. Let's play it safe there. Okay, right, identify how many bits are required for a 256 colour bitmap. Explain your answer. Okay, well, each bit, so each colour has 256 values. Okay, so it's a colour, so 256 values. Okay, so that's 0, because I have to count 0 to 255. Okay, and then basically, so 256 would be 2 to the power of 8. Okay, so that's how you would explain your answer there. Right. Okay, so let's just check the answers now. Okay, so hopefully you've written those down and you can check them against the criteria here. So as you get, there we go. Okay. Oh, I got that wrong. Oh, I'm so silly. Okay, 1 bit, of course. There we go. So even Miss Price gets it wrong. So even Miss Price, it's very late at night. So did we see that I made a mistake? What did I say in the PowerPoint earlier? Okay. Hopefully you checked that as went along that I made a mistake and you was like, well, hang on. Back in the PowerPoint. Whoops. 1 bit. 2 to the power of 1. 2 colours. How silly of me. Sorry. It's very late at night at the moment. But there we go. So that's why you need to make sure that when you do your studying, okay, that you're not doing it late at night and you're getting plenty of sleep, unlike me. Okay, so there we go. All right, so, but I got the other question right, and that was the most important one, but I almost lost myself 1 mark through carelessness. So it can happen to the best of us, guys. Right, okay, so complete your homework, please. So I've got questions on there for you, and attempt the exam questions, and then simply assess yourself according to the criteria. Okay, very best of luck to you, and have a very good, well, whenever you're watching this, very good day or a very good evening. Right now for me, it is 11:30 at night, and my brain is not working. I need to go to sleep, clearly. Okay, take care.